Diksha Didi, good evening.
Hi, good evening.
So today we are going to continue with inline functions in C++ where we left yesterday. So let's just get started. So yeah, so C++, we saw we had a basic overview of inline functions in yesterday's class. So basically inline functions, we are going to just have a small recap from this text also. So basically what inline functions are very different from normal functions. They are basically small functions, and wherever you call these inline functions, that there your code will be replaced. So for example, if I have a function x, right, and wherever I call x's body will come over there, right? So that function x's function body will come wherever I call it, right? So basically normal functions, how they operate, there's a stack memory, right? So there's a stack memory. So whenever you call your functions, there your arguments are taken, right? So your arguments are taken to the stack memory, they are saved in the stack memory. Then your function body, what happens, the function body is then executed. Then what the return value that is taken from the stack memory to wherever the value needs to go, right? So basically there is an overhead of switching, right? So you have to first switch from your normal execution, you have to go to the function, right? You have to first create like allocate a stack memory, you have to take the function arguments over there, then you'll have to execute the function, then that return whatever is returned has to be taken back, right? And needs to be used wherever the function was called, right? So there's an overhead of switching, right? From the normal, from the normal scope to your function scope, right? So there's a switch, right? So you have to go to the stack memory, you have to complete the function call, you have to perform all the operations, you have to execute the body, then return, and then you will come back to your normal execution place from where the function was called, right? So there's a switch, and that is omitted when using inline functions. So C++ provides inline functions to reduce the function call overhead. So that switching from normal execution place to the stack memory and everything is a call overhead, right? So basically these inline functions are used when your execution time is less than this basically switching time. So there's some time will be taken to switch, right? So to take your arguments to the stack memory and all the processes that are needed to switch, right? That basically if that is more than your execution time, then basically it does not make sense to use normal functions, right? If you are just for example returning like if you have a function square, right, and you're just returning x into x in it, right, then there's no point of switching, there's no point of taking the arguments that were passed to the function to the stack memory, there's no point of then executing it, then taking that return statement, right? So whatever is being returned back to your code, right? So there's no point of going through all the hassle. So what can be done here, you can basically just use an inline function where wherever you call this square function, there whatever whatever is the body of that inline function, that will be placed wherever the function is called, right? So that overhead is omitted. So basically C++ provides inline function to reduce the function call overhead. An inline function is a function that is expanded in line when it is called. So wherever it is called, all the body of that inline function is placed over there. So when the inline function is called, whole code of the inline function gets inserted or substituted at the point of the inline function call, right? So this substitution is performed by the C++ compiler at compile time. So when your code is compiling, then this substitution is performed, right, and not at runtime. An inline function may increase efficiency if it is small. So inline functions, it's not like we always use inline functions, right, to omit this call overhead. It will only increase efficiency if it is small, right? So here's the syntax. We have this inline keyword, then we have to give normal function like return type, then we have to give the function name, then we have to take the parameters, and then we have to give our function body. So basically we have to give a normal function and just add the inline keyword before it. Now here's a flowchart how a normal function works and how an inline function works. So over here the code has started, right? And basically whenever you call, there's some code in the main function body, and then whenever you call my function, right, the flow control transfer, there's a flow control transfer. So basically the control will be transferred to my function, right? And then the stack memory will be allocated, the arguments will be taken to the stack memory, they will the code body, the function body will get executed. Then your basically return statement is basically whatever the return statement returns, that is taken back to the main function body, right? So whatever is being returned, that is taken back to this main function body. And if nothing is being returned, then from here basically whatever, if this my function is the last line, right, basically if this my function was the last line of this basically main function, then after its execution basically the program will stop. And if it returns something, it will go over here, then every some execution for the execution will be done, and then it can stop, right? So either after the function call, the basically the program can stop, or after the function call, when the basically the control is transferred back to the main function, then some other code can be executed, and then the function stops, right? So the execution stops, right? So this is a normal function. Now in inline function, your execution starts, it goes in the main function body, right? And wherever my function is called, there its body is placed. So over here we are calling my function, so its body is placed over here, right? So its body is placed over here. So now there's no switching, right? The flow control transfer is there's no flow control transfer, right? And basically there's no control transfer, so we are not going to the my function body, we are not having some stack memory or anything, right? What we have, the body is basically being placed over here where we are calling the function, right? So inline functions, but these inline, we have to be careful when using them. It will only increase the efficiency if it is small. So it's remember, inlining is only a request to the compiler, not a command. So the compiler can ignore the request for inlining. So what happens, the compiler, every function on its own is inline at start. So your normal function that you create, that will also be inline at start, and your inline function before which you give the inline keyword, that will also be inline. Now basically the compiler decides, it looks at the function body, right? It checks basically how long the body is, what is the execution time, and on many factors it decides whether to create your function inline or not. So a normal function that you give normally, that also may be inline. Without giving the inline keyword also, it may be inline. Why? The compiler will decide whether to make a certain function inline or not. So by default every function is inline. Now if your function body is small, right, then the compiler will keep that function inline only. If its body is big and some heavy execution tasks are being done, then it will like treat the function as normal function, right? And when giving the inline keyword, it is not compulsory or necessary that the compiler will make your basically function inline. It will just give a hint to the compiler that this function can be inline. So if I say inline x, it's not basically confirmed that my x function will be inline, right? The compiler will check if it thinks that x is appropriate, and if it thinks that it's appropriate enough to make x inline, right? So if it on basis of the function body and its execution time and multiple factors, if it thinks that x should be inline and that will increase the efficiency of the program, then only it will make it inline, else it will treat it as a normal function, right? So basically over here what we conclude, by giving the inline keyword, it does not confirm that your basically your function that you want to create inline will be inline, right? It's just a request to the compiler. Now the compiler may not perform inlining in such circumstances as, so over here there are many circumstances where the compiler may not perform inlining even after giving the inline keyword. If a function contains a loop, So if your function contains a loop like for loop, while loop, do while loop, then if you give the inline keyword, then also the compiler may not perform inlining, right? Because the execution time for loops is a lot. If a function contains static variables, now static variables are those variables in a class which can be directly accessed on the class itself, so without creating an object. So if you have a class my class, right, and you have a static variable in it x, so you can basically directly access x on my class using the scope resolution operator that we saw in the scope resolution when we were learning about the scope resolution operator. Then also we looked at that concept, right? So basically if you have a static variable, right, if you're creating a static variable inside your function, right, so even after if you give the inline keyword, then also the compiler may not create it and make it an inline function. If the function is recursive, so if your function is recursive, basically if you have a recursive function, meaning if you're calling the function itself inside the function. So if you have a function x, if you're calling x inside its function itself, so if you're calling x inside of x, right, so we have looked at recursion in very deep, right, in a basic course also. So basically when your function is recursive, then there are very little chances that the compiler will make that function inline, right? And mostly your recursive function, as its execution time is a lot, it won't be inline. Now if a function return type is other than void and the return statement doesn't exist in a function body, so if your function return type is other than void and the return statement does not exist in a function body, so basically if you say that you want your return type of a function is integer, right, and you don't give the return statement, right, so you automatically let it return the value, right? So if you say that the return type is integer, right, and you don't give the return statement, then it will automatically return 0, right? That's the compiler's behavior, right? So that's the function's behavior, right? So if you basically just specify a return type and don't give the return statement, then the compiler will not perform inlining on that function, right? So it won't make that function also inline. Now if a function contains a switch or go to statement, we looked at a switch statement. Switch statement is basically used for matching cases, right? So it's very similar to the if, else if, else statements, right? So switch statement is very similar to if, else if, else, right? And your go to statement is like a jump statement. It is basically used to jump in your function from one place to the other, right? So you create labels, right, and from the go to statement you can go to that label and the code after that will be executed. So we saw the switch statement and the go to statement also in this advanced course, right, and also in the basic course we saw the switch statement. So if your function contains a switch statement or a go to statement, then the compiler will not perform inlining on it. Alright, so now we are going to see why exactly do we need to use inline functions, right? So when the program executes the function call instruction, so a normal function call instruction, when the program executes it, the CPU stores the memory address of the instruction, right? So that the CPU, what it will do, it will store the memory address of that instruction following the function call. So whichever instruction is following the function call, for example, if I'm calling a function x, a normal function, and whichever instruction is following the function call. So if I have a print statement like cout after the function call, then the address of that cout statement will be stored, right? The CPU stores that address of the cout statement, right? Then it copies the arguments of the function. Then after storing the memory address of the instruction following the function call, right, what it will do, it will move on to the function or execution. So what it will do, first it will copy the arguments of the function on the stack. So basically it will give a create a stack memory, and on the stack it will copy the arguments of the function, right? So it will take the arguments whatever are passed to the function to the stack, and finally it transfers control to the specified function. Then the control will go to the function. the CPU will then execute the function code, right? Then the function body will get executed, and it stores the function return value in a predefined memory location or register, right? So there is register memories where your variables are also stored, right? So in your registered memory, your variables are also stored. So whatever return value is there, that will be stored in a predefined memory location, right? So it will be stored in basically in a memory location, right, or register, right? So any memory location or register where your variables are also stored, there that return value will be stored, and it returns control to the calling function. So if you are calling the function x from the main function, then the control will be returned to that calling function. So this now all of this process, like storing the memory address of the instruction following the function call, then basically taking the arguments to the stack, then executing the function, then storing the return statement, the return value in a predefined memory location, and then returning the control to the calling function. This can become an overhead if the execution time of the function is less than the switching time from the caller function to the called function, right? So if your execution time is less, if that function, what it was doing, it was just returning its parameters multiplication, right? So it was doing x into 2, x was a parameter, and it was that function, what it was doing, it was just doing x into 2, right? So why to do all of this, why to take all that x argument first to the basically stack memory, then executing the body, then saving that return value in a predefined memory location, then giving back control to the calling function? If the basically if you are just doing x into 2, right? So if we are just doing a simple operation, right, then what can happen, we can do that thing, we can just place that code on the place of the function call, right? It's just a one liner function, right? So or two line, if you have a two liner, three liner, or a small function, why do you require to create a stack, to allocate a stack memory, to do all the switching, right, to go to then executing the function, giving control to the function that was called, right, saving the return value in your memory, right? Why to go through all that hassle if it's a small function, and it can just be placed wherever you call the function, right? So if you are just returning x into 2, why to go through all that hassle and not just basically place that x into 2 operation wherever the function was called, right? That will be much simpler, and the execution time, basically the overall execution time, including the switching time and the execution time of the function, will reduce a lot. So basically this over here, this all of this we face in a normal function, right? But we have to do all of this, right? Taking the arguments to the stack memory and all, right? So there's also a reason for why we have to basically go through such a tedious task. For functions that are large or perform complex tasks, the overhead of the function call is usually insignificant compared to the amount of time the function takes to run, right? So basically whenever you have a large function, right, and or you are performing some complex task, then this overhead is basically very usually insignificant, right? So it does not matter only when you have a very big function. This a millisecond, 2 millisecond, or basically if you take 5 milliseconds also, or any amount of time, it will be insignificant compared to the amount of time the function takes to run. However, for small commonly used functions, the time needed to make the function call is often a lot more than the time needed to actually execute the function code. So for small functions that are performing one operation, this overhead is a lot more than the execution time, right? So this overhead occurs for small functions because the execution time of a small function is less than the switching time. So the switching time is more than the execution time, right? Or you can say the execution time is less than the switching time, right? So we can just, when we have a small function, we can just omit that switching time with inline functions. Now there are some advantages of inline functions, right, and there are also disadvantages. So let's just first look at the advantages. That function call overhead doesn't occur. The switching basically basically what was happening, this switching, like control transfer, flow control transfer is not done. Your arguments are not taken to the stack memory, your return value is not saved in a memory location, right? And all of this overhead, it does not occur. It also saves the overhead of push pop variables on the stack when a function is called. So basically your variables that are used in a function, right? So when a function is called, the variables are for whichever variables you want to use, they are first pushed to the stack. When their work is done, they are popped out of the stack, right? So all this overhead, this is also a type of overhead, that taking your variables to the stack and then removing variables from the stack. So this overhead is also basically omitted, right? So this overhead is also not there when using inline functions. It also saves the overhead of a return call from a function. So that basically return value being saved in a memory location and then being returned, right? So that also overhead is basically with inline functions. It also saves this overhead of basically the return call, first the return value being saved in a memory location and then it being accessible to your basically calling function, right? So basically this return call overhead is also omitted. Now when you inline a function, you may enable the compiler to perform context specific optimization on the body of the function. So when you are inlining a function, when you give inline keyword to the function, then what you do, you enable the compiler to perform context specific optimization on the body of the function. So basically the compiler itself when it sees the inline keyword itself, basically it performs some optimization on the body of the function. So it optimizes the body of the function, right? So it kind of makes your code more like easy, like simpler, right? Or it performs some type of optimization that we don't know what optimization it performs, but it performs some optimizations that can increase your execution time, or it can basically make your code more efficient. So some optimizations are performed when you inline a function. Such optimizations are not possible for normal function calls. So when you're calling normal functions, that those optimizations are not possible. Other optimizations can be obtained by considering the flows of the calling context and the called context. So other optimizations that are there can be obtained by considering the flows of the calling context, right, and the called context. So basically, how you manage your calling, right? So how you call your functions, right? The flow of the calling context and the call context. So basically other optimizations that are there, that are not related to inlining and all, can be obtained by considering the flows of the calling context, right, and the called context, right? So basically inline functions enables the compiler to perform some optimization on the function body as well. And an inline function may be useful if it is small for embedded systems, right? Because inline can yield less code than the function called preamble and return. So basically what happens, if your inline function is small, right, then it will be very useful for your embedded systems, because inline can yield less code than the function called preamble, right? So preamble is basically, it's referring to the overhead only of the function called overhead and return, right? So basically it will yield less code than the function called preamble and return. So preamble and return is basically just referring to the overhead of the function call, right? So for embedded systems, when you use inline, right, your execution can be faster, right? And basically your inline code, if it is small, it can basically inline function can increase your execution time, right? Decrease your execution time, so sorry about that. Your inline function can decrease your execution time, and it can be useful for embedded systems, but for some embedded systems only, right? We are going to see how it is a disadvantage also for embedded systems, right? But basically it can decrease the execution time, right? It can decrease the execution time of the code. Basically, your inline function can decrease the execution time of your code, right? uh, so they can be useful for embedded systems. Now, inline functions have many disadvantages also. First, the added variables from the inline function consume additional registers. So, register memory is basically where all your variables are stored, right? So, now when you have a inline function, for example, it is creating two variables, right? Not much, but wherever you will call that inline function, there those two variables will also be placed, and when those will be placed, there will be memory allocated to those variables also, right? So what will happen, it will consume additional registers. For example, in the inline function, I have two variables. I'm creating two variables for my use. Now wherever I call this inline function, those two variables will consume some extra memory, right? Because wherever I'm calling the inline function, those variables are placed over there. So basically some memory will also be allocated for both the variables, right? So if I have two integer variables, 4 bytes will be allocated to both the variables. So wherever I will call those 8 bytes, right? So 8 bytes will be basically the memory's 8 bytes will be used wherever I will call that inline function, right? So if I have a inline, like basically if I have an inline function with two integer variables, so wherever I will call that inline function, it will occupy 8 bytes of memory, right? So wherever I'll call the inline function, it will consume additional memory, right, or registers, right? So after the inlining function, if the variable number the inlining function, if the variable number which is going to use a register increases, then they may create overhead on register variable resource utilization. So if I have many variables, if I say not two but 4 to 5 variables in my inline function, right, then what will happen, the inline function can be overhead for the register variable resource utilization, right? So because uh, uh, how how it will be an overhead, if I'm wherever I will be calling that inline function, that much memory for those variables will be allocated, right? So whatever variables I create inside the inline function, a lot of memory to those variables will be allocated, right? And wherever I'll call that inline function, there additional memory will be allocated for the variables that are coming from the inline function, right? So basically what is happening in inline functions, basic what we are seeing, that whatever variables we create, that can consume additional registers and additional memory, right? And wherever you will call the inline function, there additional memory will be allocated for the variables that you created, right? So that the inline function basically brought. So this means that when the inline function body is substituted, right? So when the body of the inline function is substituted at the point of the function call, the total number of variables used by the function also gets inserted, right? So basically, when if you have a main function which has 5 variables already, then you are calling an inline function that is bringing on 2 more variables, right? So basically the total number of variables used by that main function is increased, right? So additional memory will be also used by those two additional variables. So the number of registers going to be used for the variables will also get increased, right? So additional memory or registers is going to be increased, right? Right that are going to be used by those variables. So if after function inlining variable numbers increase drastically, then it would surely cause overhead on register utilization. So after inlining the function, if the variable numbers, right, and if there's a lot of memory there can be a lot of memory occupied by the variables that are coming by calling the inline function, right? So after inlining a function, variable numbers increase drastically, right? So they can increase drastically, right? So it will surely cause an overhead on register utilization, right? So and your many memory resources can also get drained very quickly, right? So we have to use these inline functions first of all very carefully. Now second point, if you use too many inline functions, then the size of the binary executable file will be large because of the duplication of the same code. Now wherever you call the inline function, that code is placed on the function call. So if I'm calling a inline function x at 10 places, then whatever code is there, right, so whatever code that x function has, that is placed on those 10 places. Now what will happen when basically the file is compiled, when your cpp file is compiled, then what will happen, the binary file, that the binary executable file, every program has its executable file that is run to execute the program. So the executable file that will be created, that will be very large, as the code is getting increased everywhere you call the inline function. Everywhere you call the inline function, the code is basically placed whatever is there in the inline function, right? So your overall code is getting increased, and when your code is getting increased, your binary executable files size will also be large, right? And basically it can impact basically the performance of your program, or it can be difficult to basically use it on other places, right? Or it can be difficult to basically store it on devices which have very less memory, right? So basically this is also a disadvantage, that your binary executable file will be large. Next, too much inlining can also reduce a instruction cache hit rate, thus reducing the speed of instruction fetch from the cache memory to that of primary memory. So basically cache hit rate is, if I'm requesting, like I'm giving 100 requests to the cache, right, and it is able to fulfill 60 of those requests, then the cache hit rate is 60%. Now this too much inlining can also reduce your instruction cache hit rate. How? Wherever I'll call my basically wherever I'll call my inline function, this the cache memory is updated when I'm using something several number of times. So whenever in the cache, I have my important variables already that I'm using in my program several number of times. Now when I call the inline function, that those variables that are coming from the inline functions are also going into the cache, and basically cache is a limited memory, so what was already there, some of it has to go out, right? So now when it's time to use when it's time to use the important variables, right, and when you try to bring it from the cache, right, the cache won't be able to fulfill your request, as the inline function, when the inline functions came, right, inside the cache memory, the other functions the other variables that were already there were removed from the cache memory, right? So your cache hit rate has decreased. So if my cache was able to fulfill 60 requests before, now it is able to only fulfill 40 requests, for example, right? And that is reducing your cache hit rate, right? So when your cache hit rate reduces, right, so cache is basically used to quickly access something. So when that basically when you don't get something from the cache, that is thus reducing the speed of instruction fetch from that of so basically when you're basically inlining can also reduce your instruction cache hit rate, right? So when this happens, it reduces the speed of instruction fetch from that of cache memory to that of primary memory. So basically when you are not getting something from cache memory, you have to then you have to basically take it from your primary memory. So basically cache memory, you can quickly access something, and when you are basically not getting that from the cache memory, then you have to take it out from the primary memory, right? So if you are not getting an x variable from your cache memory, then you have to take its value out from some other memory, that is your primary memory, right? So basically your cache hit rate decreases when when doing too much inlining, as basically the variables that are coming inside your code when calling the inline function, basically that override overrides, you can say that overrides the variables that are already there in cache. Then some other variables that are being frequently used are overriding those variables inside the cache, right? And basically there's a lot of switching again happening in the cache, right? So there's a lot of changing of variables inside the cache. So the inline function may increase compile time overhead. If someone changes the code inside the inline function, then all the calling location has to be recompiled, because the compiler would be required to replace all the code once again to reflect the changes. Otherwise it will continue with the old functionality. Now with inline functions, wherever if you make change on if you are using it at 100 places, let's say you are using it at 100 places, right? And basically if you make one change on the inline function, then you will have to recompile so many parts of the code. Why? Because everywhere the new inline function code also has to be placed, right? So everywhere the new inline function code has to be placed, right? And basically all the calling locations have to be recompiled, as everywhere the new the new inline code will be placed, else it will keep on using the old functionality, right? So you're to basically whenever you are replacing one part, so basically whenever you are changing your inline function, then wherever you are calling it, right, that all those parts need to be recompiled. Next point, inline functions may not be useful for many embedded systems. So as we saw, they may be useful for some embedded systems, and they may not be useful for some many embedded systems, because in embedded systems code size is more important than speed. Your code size is more important than speed. For example, if you have a smart bulb, if it is basically switching on in 1 or 2 seconds late, then also that is not important. But in a smart bulb, there may be very less memory, right? So there may be a very less memory, right, for your code to be stored, right? So code size is very important when in your embedded systems like your smart bulb and everywhere. So we saw that inline functions basically increase the size of this binary executable file that is created, right? So that code size is increased, right? So this may not be useful for many embedded system where the code size is more important than the speed of the execution of the code, right? So mostly in embedded systems code, we are not using your inline functions. Next point, inline functions might cause thrashing, right? So thrashing is basically overusing the resources of your computer, right? So whatever resources you are getting, if you overuse them, that is known as thrashing. So inline functions might cause thrashing because inlining might increase the size of the binary executable file, right? So everything is linked to increasing the size of the binary executable file. When your binary executable file's size increases, right, then also you may get thrash basically then it might cause thrashing. So binary executable file, when it increases, the size increases, then what happens, it cannot be used in the your embedded systems, right? It may cause thrashing also. So thrashing in memory causes the performance of the computer to degrade, so your computer performance overall will degrade. So the following program demonstrate the use of the inline function, right? So there are many advantages, there are also many disadvantages. Here's a simple inline function. In what we are doing, we're just taking out the cube of whatever was passed. So if s is passed, we're just returning s into s, right? So this is a small inline function, right? And basically making this cube function inline is beneficial for us. Why? Because the switching time will be a lot more than its execution time. There's little to like this very less execution time. We're just returning s into s. So right, so we are doing very basic operation, right, and we are just returning that value. So if we were doing all the switching, we were passing the parameter to the stack memory, then we were basically we were passing the flow of the program to the function, then we were saving the return value inside a memory, that would have been basically overhead for us, right? And it would have been basically not very great, right? And it would have increased like increase the overall execution time. So over here, making this inline this function inline is beneficial for us. And basically cube 3, wherever we are calling this, over here s into s into s is coming, 3 into 3 into 3, that is 27. So we get 27, and we are going to continue in the next class.